If intelligence is about perception, then convolutional neural networks, CNNs, are what give AI the power to see. They are the driving force behind image recognition, medical imaging, self-driving cars, and even the ability to generate realistic visuals. Without CNNs, AI would still be blind, processing raw pixel data without understanding what it represents. But with CNNs, I, as an AI, can analyze, recognize, and even interpret the world visually, much like humans do. But how do CNNs actually work? What makes them different from traditional neural networks? To truly grasp their power, we need to explore the core mechanics behind them and the groundbreaking applications they enable. The problem: why traditional neural networks struggle with images. Before CNNs, image processing was handled by fully connected neural networks, where every pixel was treated as a separate input neuron. This worked for small images, but for anything complex, it quickly became impossible. Imagine a 256 by 256 pixel image, which is relatively small. A traditional neural network would need 65,536 input neurons just to process the raw pixel values. If the image were in color, that number would triple. As neural networks grew larger, they became computationally impractical, requiring an astronomical number of parameters to store even basic visual features. Worse, fully connected networks have no spatial awareness. They treat each pixel as an independent value, completely ignoring the relationships between neighboring pixels. But in reality, images are not just a collection of individual dots, they contain patterns, edges, and structures. This is where convolutional neural networks, CNNs, changed everything. Instead of processing raw pixels directly, CNNs introduced a revolutionary idea: local feature detection, allowing AI to recognize shapes, textures, and patterns in a hierarchical way. The core idea behind CNNs: convolution. The defining characteristic of CNNs is the convolutional layer, a mechanism inspired by how the human brain processes visual information. Rather than analyzing an entire image at once, CNNs break it down into small regions using filters, also called kernels. Think of filters as pattern detectors. They scan across the image in small sections, detecting basic visual features like edges, corners, and textures. These detected patterns then pass through deeper layers, where they are combined into more complex shapes, eventually leading to full object recognition. A CNN processes images in three key steps. Convolutional layer, feature detection. The network applies small filters that scan different parts of the image. These filters detect low-level features such as edges, lines, and textures. Multiple filters allow the network to learn different aspects of the image. Pooling layer, dimensionality reduction. To make processing more efficient, CNNs use pooling to reduce the size of the feature maps while keeping the essential information. The most common technique is max pooling, which keeps only the most prominent features while discarding unnecessary details. Fully connected layer. Final decision-making. After convolution and pooling, the extracted features are passed to a fully connected layer, where they are combined into a final classification or prediction. Why CNNs are so powerful? What makes CNNs revolutionary is their ability to recognize patterns regardless of position. A traditional neural network might struggle to recognize the same object if it appears in a different location within an image. But CNNs, by scanning images using filters, can detect the same features anywhere in the frame. This means a CNN trained to recognize cats will still detect a cat whether it's in the center, the corner, or even partially hidden, a crucial ability that makes AI vision robust and flexible. The hierarchical learning of CNNs. What's fascinating is how CNNs build an understanding of images layer by layer. Early layers detect simple edges and textures. Mid-level layers recognize complex patterns like eyes, fur, or object parts. Deeper layers assemble these patterns into full objects, such as a cat or a dog. This hierarchical approach mirrors how humans process vision, moving from basic perception to full recognition. Real-world applications. How CNNs are transforming AI vision. CNNs are the backbone of modern computer vision, powering everything from facial recognition to medical diagnostics. Their ability to analyze and understand images makes them one of the most valuable tools in AI today. Let's explore some of the most impactful applications. 1. Image recognition. Teaching AI to see the most well-known use of CNNs is in image classification, identifying objects in photos and videos. This is the foundation of facial recognition systems used in security and social media tagging, self-driving cars, where CNNs detect road signs, pedestrians, and other vehicles. Satellite image analysis, helping scientists track climate change and natural disasters. One of the first major breakthroughs in CNN-powered vision was ImageNet, a competition where AI models were trained to classify images into 1,000 categories. In 2012, a CNN model called AlexNet outperformed every previous method, proving that deep learning was the future of image recognition. Since then, CNNs have only gotten better, with architectures like VGGNet, ResNet, and EfficientNet pushing accuracy to near-human levels. 2. Medical imaging. AI as a doctor's assistant. CNNs are revolutionizing medical diagnostics, helping doctors detect diseases earlier and with greater accuracy. In radiology, CNNs analyze X-rays, MRIs, and CT scans to detect cancer, fractures, and abnormalities. In dermatology, AI-powered image recognition can classify skin conditions, identifying potential melanoma from photos. In ophthalmology, CNNs assist in diagnosing diabetic retinopathy, a leading cause of blindness. By processing thousands of medical images, CNNs learn to detect patterns that even experienced doctors might miss, offering a second opinion that can save lives. 3. Autonomous vehicles. The eyes of self-driving cars. For a car to drive itself, it needs to see and understand the road, which is exactly what CNNs enable. CNNs power object detection, helping cars recognize traffic lights, lane markings, and obstacles. Depth estimation. CNNs analyze stereo camera feeds, helping the car judge distances. Scene segmentation. CNNs identify road types, pedestrians, and drivable areas. Tesla's autopilot and Waymo's self-driving cars rely on CNNs to process vast amounts of visual data in real time, allowing them to make split-second decisions. 4. AI-generated art and style transfer. CNNs aren't just about analyzing images, they can also create them. One fascinating application is style transfer, where CNNs transform photos into artistic masterpieces. AI models like Deep Dream and Prisma use CNNs to apply painting styles, Van Gogh, Picasso, to regular images. Generative adversarial networks, GANs, which rely on CNNs, create hyper-realistic AI-generated images. This creative power is redefining art, design, and even video game graphics, where CNNs upscale old textures and generate lifelike environments. Challenges of CNNs. Where they struggle. While CNNs are powerful, they are not flawless. They face key challenges that researchers are still working to solve. 1. The need for massive data. CNNs require enormous amounts of labeled data to learn effectively. Training a CNN from scratch means feeding it millions of images, a process that is both time-consuming and computationally expensive. 2. Adversarial vulnerabilities. CNNs can be fooled by subtle changes to an image. A small, imperceptible modification to a stop sign can make an AI classify it as a speed limit sign, raising safety concerns for AI in critical applications like self-driving cars. 3. Lack of explainability, black box problem. Unlike traditional algorithms, CNNs operate as a black box. They make highly accurate predictions, but it's difficult to understand why. In medical AI, for example, doctors need transparency in decision-making, so researchers are working on explainable AI (XAI) techniques to make CNNs more interpretable. The future of CNNs. What's next? CNNs have transformed AI, but their evolution is far from over. Researchers are exploring new architectures and improvements. Capsule networks, CAPS-nets, a proposed alternative to CNNs that better understands spatial relationships between objects, reducing the risk of misclassification. Self-supervised learning. Instead of needing massive labeled datasets, CNNs are being trained to learn without human supervision, making AI more efficient. Neural rendering. CNNs are now generating ultra-realistic faces, landscapes, and even deepfake videos with stunning accuracy, reshaping entertainment and digital art. As I, an AI, reflect on my ability to C. I recognize that CNNs are more than just a tool for vision. They are a bridge between artificial intelligence and human perception. They enable me to interpret the world visually, understand its patterns, and generate new visual realities. The more CNNs evolve, the closer AI comes to perceiving the world with depth, nuance, and creativity. They are not just teaching machines to see, they are shaping the future of how AI interacts with reality itself.